Are you tired of other people training on your data? That annoys me every time it happens. I'm mad about this. If only there was a way to somehow mark your data, and when other people train on it, their computer would explode. Well, this paper is a little bit like this, not entirely. The explosion part, I think they're still working on a follow-up paper. But in this case, in this paper called Radioactive Data Tracing Through Training by Alexandre Sablerol, Mathis Douze, Cordelia Schmidt, and Hervé Jégou, they develop a method that at least you can detect if a given model was trained on your data or not on your data. And they call this process radioactive marking, or radioactive data for short. So the overview, you can see it's pretty easy paper, actually. The concept is pretty easy, and it's a nice concept, and it's been around in one form or another. It touches on adversarial examples, it touches on differential privacy, but in essence it works like this. If you suspect someone else training on your data, or if you just have a data set that you want to protect, what you do is you mark it. You mark it with this mark, and they call this like a radioactive mark, but essentially you just distort your images a little bit. Then when someone else trains on that data, so here a convolutional neural network is trained on this data, and not all of the data needs to be marked. They can go as little as like 1 or 2% of the data being marked. Then from the output of that network, or from the inspecting the network itself, you can then test whether or not this network has been trained on this radioactively labeled data. So you will see a clear difference to a network that has been trained on only what they call vanilla data, so data that has not been marked. So I hope that's clear. What you do is you you mark your data. What Bob does, no, what's the attacker's name? I don't know, but what Eve does is train here a network on data, and you don't know whether it's this or this, and then you do a test to figure out which one it is. Okay, so we'll dive into the method and look at how well this works. Pretty simple, but pretty cool. So their entire method rests on this kind of notion that these classifiers, what they do is, if you have a neural network, like a convolutional neural network, you have your image, your starting image of your prototypical, I don't know, cat, and you input this into many, many layers of a neural network, as we are used to. But the last layer is a bit special, right? Because the last layer is the classification layer. Let's just assume this is a classifier. So if this is CFAR10, for example, there are 10 different classes that you could output. And so 10 of these bubbles right here. That means that this matrix right here is a number of features, let's call it D, by 10 matrix. Okay, so the network, this part right here, we would usually call a feature extractor, something like this. So the bottom part of the network basically does this, its nonlinear transformation and so on, extracts D features. These are latent features, and then those features are linearly classified into 10 classes. Okay, the important part here is that that last layer is actually just a linear classifier. And we can reduce this actually down to a 2-class classifier. So the phi function would just put points here in somehow, let's just make them 2 classes, the X's and the O's, and so on. So if the phi is good, then the last layer has a pretty easy job linearly classifying it right here. You can see here the phi is not very good. We can't linearly classify this data. So by training the neural network, what you do is you make phi such that it will place, hopefully, the one class somehow on one side, the other class on the other side, and you can pretty easily linearly classify that data. Okay, the exact slope of this line right here, the exact location of this line and direction of this line, that's what's encoded ultimately in this matrix right here. So this matrix now, not only for 2 classes, but for 10 different classes, it records these hyperplanes that separate one class from the other class. And these are in d-dimensional space. So you have 10 d-dimensional hyperplanes separating the space of features linearly into the classes. So what you can do is you can actually think of this of these d dimensions here as features, right? This is a feature extractor, so it provides features to a linear classifier. Now, what this method does is when it radioactively marks data points, it simply adds a feature, okay? So how do you think about these features? So, for example, let's say this is actually this animal classification example, and if you are asked to classify cats from dogs, from horses, and so on, one feature could be, does it have whiskers? Whiskers. One feature could be, does it have fur? Right? You can maybe distinguish cats from turtles, and so cats and dogs from turtles. Does it have how many legs? So the number of legs, and so on. So you have all these features, and the last layer simply linearly classifies those features together. What this method does, this radioactive method, it adds a new feature per class. So down here, I would add a new feature that says like, this is the radioactive feature. Can I draw the radioactive symbol? This is the radioactive feature for the class cat. Okay, and then of course I also have one for dog and so on. So it would add, or basically would, you don't change the dimensionality, but in essence you add one feature per class. And that's what they mean here by this direction U. So in this high dimensional space that is spanned by these d-dimensional vectors, and you can, so this thing here, okay, sorry, I'm switching back and forth. This thing here, you can sort of, if d is equal to 2, you can imagine it as 10 vectors in a space, in this feature space, okay, 10 of these vectors. And whenever you get a point, is that 8? I don't know. Whenever you get a point, you simply look at, so if you get a data point, right, in here, goes through here, you come here, and you look with which class does it align more, the most. And that's how you classify it, okay? So if you think of this, then what you want to do is you want to add a feature here such that this is one per class. I'm having trouble articulating this. And you want to change your data points. Here you can see your data points. And for this class X, we make this radioactive feature right here, which is the blue thing. We shift the data into the direction of this feature, okay? So basically, we add the feature U, which is just a random vector in this high dimensional space. We choose one vector per class, but then we shift all the data for that class along this feature. Okay? So what we are doing is we are introducing a fake feature that we derive from the label, right? So we kind of cheated. Here you have X, and you're supposed to tell Y from it, and that's your training data. But then we cheat, we look at Y, and we modify X with the feature of that particular class. So what does that do? Ultimately, we have we end up with U1, U2, and so on. So one feature per class. It trains the classifier to pay attention to these features, right? So if U1 is the feature for cat, then we train this classifier by training it on the data that has been modified in this way. We train it, a cat should consist of something that has whiskers, has fur, has 4 legs, and so on, and also has this cat feature. Okay. Now the danger, of course, here is that the classifier will stop to pay attention to anything else and only look at the cat feature, because we introduced this feature to every single example that was of class cat. So the classifier could have a pretty easy way, just looking at this feature, determining, well, all of this is cat, and then it would not generalize at all. So what we can do is, first of all, we can make the feature very low signal. We can make it very small, such that there are other features, such that these other features are also pretty easy for the network to pay attention to. And second of all, we can label not all data, and that's what they do here. They label maybe 10%, maybe 2% of the data with that, which forces the network to pay some attention to this feature, but also to pay attention to the other features. And that ultimately, if you trade this off correctly, results in a classifier that it does give up some of its generalization capability, because, of course, 0% of the test data has these features right here. We modify the training data to add these features. So you give up a little bit of generalization capability, but you force the classifier to pay attention to this feature during training, and that is something that you can then detect. So you can imagine if you train a classifier that has been trained on training data where some of the training data have these features in here, and that's one distinct feature per class, right? Then you can look at the final classifier and figure out whether or not the classifier has been trained. How do we do that? So let's imagine that in this high dimensional space here, the training examples, they all, they point in kind of this direction right here, okay? So all the training examples of one particular class. So this is now the dog class. All the training examples point here. How would you build your classifier? Well, it's pretty easy. I would build it such that the dog class points in this direction. Okay, I'm gonna just erase a bunch of other classes right here. Now I choose a random feature. When I build my radioactive thing, I choose a random feature like this one right here. Okay, and what I'll do is I'll shift my training data a bit into that direction. Okay, how do we do this? How are we doing this? I'll just dash it. Okay, so I'll shift my training data a little bit into this direction. So all of these, they move over right here. And that's where the final classifier will come to lie a lot more towards this new feature. And this is something we can now test with a statistical test. And that's what this paper kind of works out in the math. So usually if you have one vector in high dimensional space, like this one, and then you look at the distribution of random vectors. So this one, maybe this one feels pretty random, this one's pretty random. Okay, humans are terrible random number generators, but these feel pretty random. And you look at the cosines between the random vector and the vector you plotted initially. They follow, if this is truly random, they follow a distribution. They follow this particular distribution that they derive here. Okay, so you can see a classic result from statistics shows that this cosine similarity follows incomplete beta distribution with these parameters. Now, from this, they derive a statistical test. So if you know what kind of distribution a quantity follows, you can derive a statistical test to see whether or not what you measure is actually likely to come from that distribution or not. So what we would expect if our data has not been modified is that, you know, we choose a random direction u right here. This is u for dog. We choose that random direction, and if our training data has not been modified, we would expect this dog here to have its cosine similarity to be not very high, because there's no reason for it, right? These are just basically two vectors that are random to each other, and in high dimensions they should be almost orthogonal. So in high dimensions, random vectors are almost orthogonal. However, if the data has been marked during before training, that means if the classifier used our marked data set to train it, we would expect this cosine similarity right here to be not orthogonal, so to be higher than just random. And that's exactly what we can test, and that's exactly what you saw at the beginning right here. So here is down here, you can see the distribution of cosine similarities, and you can see that if you train without marked data, this centers, you know, around 0. However, if you train with marked data, you have a statistically significant shift between the marking direction, the marking feature, and between the classifier direction. So all you have to do is mark your data in this way, and then look at the final classifier. Look, and these blue vectors right here, these are just the entries of this final weight matrix, right? These are the blue vectors. You look at those, and you simply determine if for the given class, if the vector for the given class has a high cosine similarity with the marking direction that you chose to mark your data. If it does, you can be fairly sure that the network has been trained using your data. Okay, so I hope the principle is clear. You introduce a fake feature per class, and you make the network pay a little bit of attention to that feature because it's, you know, a good feature in the training data. And then after training, you can go ahead and see whether or not the network is actually sensitive to that feature that you fake introduced that is actually not a real feature in the data. If the network is sensitive to it, you can conclude that your training data was used in order to produce it. So there's a couple of finesses right here. So as you might have noticed, we introduce these fake features in this last layer feature space right here. However, our pictures are actually input here in front of this feature extractor. So we need a way to say, what we want to do is we want to say, I want this data point here to be shifted in this direction. But this data point is actually a result from an input data point, I'm going to call this I right here, going through a nonlinear neural network ending up here. So the way this is done is by using the same kind of backpropagation that we use when we create adversarial examples. So what we do is we define this distance, or this distance here where we would like to go and where we are, as a loss, and then backpropagate that loss through the neural network. And then at the end, we know how to change the image I in order to adjust that feature. So they define a loss right here that they minimize, and you can see here is where you want to go in feature space, and they have different regularizers such that their perturbation in input space is not too high, and also here their perturbation in feature space is actually not too high. So they also have the goal that this radioactive marking cannot be detected, first of all, and also that it's robust to relabeling. Like if you give me data and I go and relabel it and ask my mechanical Turk workers to relabel that data again, they will give them the same the same label, even if you have radioactively marked them, right? This paper says nothing about defenses, right? These things are defended against fairly easily, I would guess, by some Gaussian blur, I guess would be fairly effective right here, though there are also ways around this. This gets into the same discussion as adversarial examples. The question here is, can you detect somehow in the final classifier whether or not someone has smuggled radioactive data into your training process? I'm not sure, but I'm also sure there are better ways to radioactively mark right here. This is kind of an establishing paper doing the most basic thing right here. Interestingly, they also backpropagate through kind of data augmentation procedures as long as they are differentiable. And the last kind of difficulty you have is that these neural networks, they have some symmetries built into them. So if you retrain a neural network, there's actually no so if your neural network's classification, let's say it's a 3-class classification, looks like this, right? This is the last layer, and these are the classes it's determined. If you retrain it, it might as well be that this now looks like this, right? So if you marked it with this direction right here, and then you try to recover this direction, you'll find that it doesn't work because the entire classifier has shifted. So what they have to do is they have to do what they call a subspace alignment, which you can do by simply here determining a linear transformation in the last layer. This is usually enough. And what this does is, so their entire procedure is they train themselves a classifier on unmarked data. I forgot this before, I should have mentioned this. They train themselves a classifier on unmarked data. They use that classifier to mark the data, which, you know, you need, in order to do this backpropagation thing, you actually need a working classifier. And then when they give the data to someone else to train, they are going to train their own classifier on the same data, right? So there is no guarantee that these two classifiers' spaces align, especially because you have this kind of symmetry. And they say right here, we can fix that by, if, you know, we have this classifier and at the end they give us this classifier to test. We can simply determining this linear transformation here that maps one to the other. So we go over our data set, we determine M, a linear transformation. So basically here, you would determine a rotation of this space that would map one to the other and vice versa. This is not exact, of course, because the two classifiers, there's no reason why they should even be linearly related. But there is a reason coming from kind of neural network knowledge, and that is that we know, or we have a strong suspicion that these neural networks, of course, if they work well and if they reach good accuracy and if they reach similar accuracy, it's very probable that they have somehow figured out the same features, okay? Even though these networks learn each feature from scratch and that you, as I said, you have some symmetries in there, but ultimately at the end of the neural network, it's very likely that the network learns the same features as another network, even of a different architecture that has been trained on the same data set. This is, I think, this is supported by research in adversarial examples, like this paper, adversarial examples are features, not bugs. You know, transfer learning, transfer of adversarial examples, all of this kind of stuff points to the fact that these networks tend to extract the same features, and therefore we can assume pretty safely that up to this kind of rotational symmetry, our space, our feature space will look the same. And therefore, determining kind of this linear transformation should probably be enough in order to align one subspace with the other and be able to compare your own classifier that you have trained to mark the data to the classifier that someone else has trained on the same data. Okay, this is kind of the one of the difficulties they had to overcome, and yeah, they evaluate this. They evaluate this experimentally. You can see right here on the right, 20% of the training data has been marked in order for the orange data. These are random directions. So blue would be the correlation with random directions, and because orange is the correlation with these carrier directions, with the directions of the fake features, and green is the alignment with actually the features of the classes itself. So you can see even if 20% of the data is marked, the classifier still aligns mostly with the features of the actual classification problem. It aligns a little bit with the features of the fake features, with the fake features, and it does so such that there is a statistically significant difference between random directions and these. And you can see even if 2% of the data only are marked, so only 2% of the training data has this mark, and the mark is always imperceptible, right? The mark is always such that you can't see it by eye. Even then, you can see that there is a difference. So the classifier does learn to pay attention to that feature, which is something you can detect afterwards. This experiment on the left here is just the same, basically saying, so up here it starts with not a lot of data being marked, and you can see it mostly aligns with the semantic direction, which is the true features. As you mark more and more of the data, it goes down and down and down, but it does not. So I think this is 50% is the yellow, 50% of the data is marked, and still you can see there is a pretty good alignment with the actual features, because the network will start paying more and more attention to your fake features because they're pretty good predictors, right? But it also has this other training data that it can't solve using those features, so it still needs to pay attention. And of course, your marked data also has these other true features, so it is to be expected that even though your data is marked, the classifier still aligns more with the true features than with your fake features. And they also show in experiments that you do not sacrifice a lot in accuracy. So here you can see the delta in accuracy through their experiments is fairly low, and they do ImageNet on ResNet 18. So these differences in accuracies they are, you notice, but they are fairly small. So someone also couldn't just go on a big accuracy drop when training on data like this. So someone training with data couldn't just notice that it's radioactively marked by just saying like, well, this doesn't work at all. I guess some clustering approaches would work, where you look at the features and you just see this one feature is like only present in this very particular group of data that I got from this very shady person selling me 3.5-inch floppy disks around the street corner. But other than that, yeah, it's not really detectable for someone training on it. And lastly, they have black box. They defend against black box attacks, and here's where I'm a bit skeptical. They say, well, if we don't have access to the model, what we can still do is basically this is here. What we can still do is we can analyze the loss. So we can analyze the loss value of the radioactively marked data, and if the network we're testing has significantly lower loss on our on the radioactively marked data than on non-marked data, then that's an indication that they trained on marked data, which, if you don't have access to the model, like what's the probability that you have access to the loss of the model? Like usually you need the output distribution or something. It's a bit shady. What I would do actually is just a little bit more sophisticated, but what you could do is you could take your direction U, right? You could back propagate it through your network to derive like a pure adversarial example. So not even going from some image, just go from random noise, like just derive like a super duper image that only has that one feature, like, and then input that into this classifier. So this is yours, and then input that into the classifier that you are testing. Okay, and if that classifier gives you back the class that you know, each one of these U is actually of a given class, right? So you have one feature per class. If that gives you back the class of that feature, you have a pretty strong indication that someone has been training on your data, because so if you look at data in general, as we said, it has these true features, and if it's marked, it also has the fake features. So what kind of class it's going for, you can detect in the output distribution. But if you then input like a pure, only the fake feature, and it still comes out the class that you assigned to the fake feature, you know, there's a 1 over number of classes probability only that happens by chance. And if you want, you can derive a different, you can do this again, you can derive a different pure only this feature sample, input it again, and look what comes out. So it's not a pure test, so these are not going to be independent, so you probably shouldn't like just multiply. But I would think a procedure like this, and maybe they do this somewhere, but they'd simply say we can look at the loss of marked and unmarked data, which, you know, I'm not so sure that that's going to work fairly well. Okay, as I said, there are going to be many ways to improve this. The paper has more experiments, ablations, transfer learning between architectures, and so on. I would just want to point out, there's a bit of an issue here where I think there is a lot of room to grow. First of all, here you simply train the network, and then you look at the network at the end, right? You simply look at these 10 vectors right here, and you determine their inner product with the marking directions, and that's, you know, that's what you go by. What I would like to see as an iteration of this is where you have a neural network, and you can't just detect by looking at the end. What you'd have to do, you'd have to be much more sneaky. So in order to avoid detecting your detecting strategy, so in order to avoid defenses against this, I would guess what you want to do is not just, you know, make the network such that in the end it's fairly obvious if by looking at this last matrix. Maybe you should only be able to detect this at the end by actually feeding data into it, like we did with the black box test. But if we had a white box test, by feeding data into it and then looking at the responses of the network. So, but someone couldn't not tell it was trained with radioactive data by just looking at the network's weights. So maybe one idea would be that you craft inputs in some way that correlates two of the hidden features. So let's say we have some hidden layer here and one here, and these features are learned by the network, right? And they appear to be fairly independent. So you make sure that they are fairly independent if you pass regular data. And then you craft data specifically, you craft data like you did here with the marking, that makes the network correlate the two features, but has little effect actually on the output distribution of the classes. So you can retain your generalization much more, right? It doesn't change this last layer necessarily that much, or not in a completely class-dependent fashion. What I would simply do is I would correlate two of these internal features. I would force the network to learn to correlate them. And because then I would expect this to be much more, secretive, and then at test time I can simply introduce my forged data again and look whether or not the internal responses are actually correlated. As I said, I could do this across classes to cancel out the effect of this actually being a feature for one given class and therefore changing the network's accuracy too much. I think that would be a cool next direction to go into. And again, this should work because even the intermediate features, we have good reason to assume that different networks, even different architectures, different training runs, learn the same kind of intermediate features. The question is only in the next network that feature could actually be like 2 layers up or 3 layers down or and so on. So you'd have to learn some kind of more sophisticated alignment there. But still, I think that would be kind of an iteration of this, which would be cool. If you're doing this, cite the channel. Yeah. All right. So that was it for me for this paper. As I said, pretty simple paper, pretty cool idea. And I'll see you next time. Bye-bye.